Hello, my dear children. Welcome back. I know, exams are just around the corner and there's a lot of tension, right? But listen, you don't have to worry one bit. Today, we're going to tackle metals and nonmetals, and I promise we'll make it so simple that you'll never forget it. And hey, if you find this useful, do me a small favor. Hit that subscribe button and share it with your friends. Your comments really make my day. All right, so here's our game plan to absolutely conquer this chapter and get you those full marks. First, we'll learn how to spot metals and nonmetals. Then we'll see how they behave, how they react. We'll climb the reactivity leaderboard, which is super important. Then a little story about ionic bonds, how we get metals out of the ground, and finally, the most important part, we'll tackle some exam questions. Ready? Let's go. Cello? Okay, first up, Section 1, Spotting Metals and Nonmetals. Let's put on our detective hats, shall we? Think of it like an identity parade. We're going to look at the clues, their physical properties, to figure out who's a metal and who's a nonmetal. So, how do you actually spot a metal? Well, it's pretty easy, really. For starters, they're shiny, right? That shininess has a special name, luster. They're generally hard. You can also beat them into thin sheets or draw them out into long wires. And you know that ringing sound your school bell makes? That's called being sonorous. Plus, and this is a big one, they are fantastic conductors of heat and electricity. Let's zoom in on a couple of these properties. First up, malleability. Now, it sounds like a big, difficult word, but it's not. It just means you can hammer a metal into a super thin sheet. And you see this every day. Think about the aluminum foil your mom packs your tiffin in. That's malleability right there. And the next one is ductility. This is the amazing ability of metals to be stretched into thin wires. And get this is an absolutely mind-blowing fact. Just 1 gram of gold, 1 single gram, can be drawn into a wire 2 kilometers long. Can you believe that? It's incredible. And this property is exactly why we can have all those copper wires running through our homes, bringing us electricity. Okay, now everyone listen very carefully. This slide is, let's call it a 5-star, super important slide. Why? Because examiners absolutely love asking about these guys, the rule breakers. For example, mercury is a metal, but it's a liquid. And sodium, it's a metal, but it's so soft you can cut it with a knife. On the other side, you have iodine, a nonmetal that's shiny, and graphite, which is a form of carbon, a nonmetal, but it conducts electricity. Please remember these exceptions. They are almost guaranteed to show up in your exam. All right, let's move on to Section 2. So far, we've talked about what metals look like. But now for the really fun part, how they act. We're going to see what happens when metals get into some action with other elements. This is where things get really interesting. So let me ask you a question and get your brains working. What happens when metals meet oxygen? When you burn them or just leave them out in the open air. Think about an old iron gate that's gone all rusty. What do you think is actually happening there? Well, almost all metals will combine with oxygen to form something called a metal oxide. But here's the catch. They don't all do it in the same way. Not at all. You have metals like sodium and potassium that are so hyperreactive, they literally catch fire. That's why they have to be kept under kerosene oil. Then you have copper, which just gets a dull black coating. And then there are the VIPs, gold and silver, who are just too cool to react, even at high temperatures. See, this is already giving us a big clue that some metals are way more reactive than others. And you know what? It's pretty much the same story with water. Sodium and potassium, they go absolutely ballistic, even in cold water. Magnesium is a bit more demanding. It says, nope, only hot water for me. Then you have aluminum and iron, who are even fussier. They will only react with steam. And of course, gold, silver, and copper just sit there, not reacting at all. So all these reactions are giving us clues about which metal is the most powerful, right? And all these clues, their reactions with air, with water, they all lead up to this. This is probably the most important part of the entire chapter, my children. It's the reactivity leaderboard, what we officially call the Reactivity Series. This is where we finally find out who is the real king. Ta-da! Here it is, the leaderboard itself. Now, listen to me, you have to learn this series by heart. No excuses. You can see potassium, K, right there at the top. He's the king, the most reactive. And as you go down the list, all the way to gold at the very bottom, the reactivity keeps decreasing. Trust me, this series is your secret weapon, your key to solving a ton of questions in your exam. So, what's the whole point of this leaderboard? Well, it gives us one simple golden rule. Ready? A more reactive metal, one that's higher up on the list, can kick out a less reactive metal from its salt solution. It's like in a wrestling match. The stronger wrestler always wins, right? It's the same idea here. And we call this a displacement reaction. Okay, let's move on to our next section. Now we're going to see what happens when a metal and a non-metal meet. How do they actually react with each other? To understand this, let's just think of it as a simple story. A story of friendship. A friendship of give and take. So picture this. You have sodium, who is a very generous friend. He has one extra electron that he's just dying to get rid of. And then you have his friend chlorine, who is in desperate need of just one electron to feel complete and happy. So what do you think happens? Of course, sodium generously gives his extra electron to chlorine. And this simple act of giving and taking, that's what forms their bond. And this give and take of an electron creates a really, really strong attraction between them. It's like they're best friends now. This is what we call an ionic bond. And the compounds formed this way, like our normal table salt, sodium chloride, they have some very special properties because of the strong bond. They're hard solids, they have very high melting and boiling points, and, this is important, they conduct electricity only when you melt them or dissolve them in water, not when they are solid. You guys are doing great, really. We're almost there. Now for a quick peek into how we get these super useful metals from deep inside the Earth, and then how we protect them. It's the story of their journey, from the Earth right into our homes. So this whole process of getting metals from the Earth is called metallurgy. Now don't get scared by the big word or the steps. You just need to understand the basic idea. Think of it like this. First you find the rock with the metal in it. That's the ore. And you clean it up, removing all the dirt and sand. Second, you extract the metal from that cleaned up ore. Third, you get the crude metal out of that. And finally, the fourth step is refining, which is like polishing it to make it super pure. So basically, clean, extract, get the metal, and purify. Simple. But wait, our job isn't done. Once we have the pure metal, like iron, we have to protect it. From what? From corrosion. Rusting. So how do we stop it? Well, you see the answers everywhere. You can simply paint it, right? Like our gates and window grills. You can put a layer of oil or grease. You can do something called galvanizing, which is just coating it with a layer of zinc. Or you can mix it with other metals to make an alloy, like the stainless steel your spoons and plates are made of. All right, we've made it to the final section. And this is where we put everything we've learned to the test. It's time to practice with some actual exam-style questions. Let's do this and make sure you are all set to score full marks. Cello! Okay, here's the first one. This is a classic question, an examiner's favorite. Why is sodium kept immersed in kerosene oil? Come on, think back. Remember that reactivity leaderboard. Where was sodium on that list? What did we say about how it reacts with air? And the answer is because sodium is super, super reactive. It's right near the top of our leaderboard. It reacts so violently with the oxygen and moisture that's just floating around in the air that it will spontaneously catch fire. So the kerosene oil acts like a blanket, a shield, keeping it safe from the air. See? Simple. Ready for the next one? This one is a little trickier, but equally important. The question is, what are amphoteric oxides? Now, think about it. We learned that metal oxides are generally basic in nature. But I mentioned there are some special ones, some with a dual personality. Do you remember? So here's the answer. Amphoteric oxides are those clever metal oxides that can react with both acids and bases. They're like chameleons. If you put them with an acid, they act like a base. If you put them with a base, they act like an acid. And the two best examples you must remember for your exam are aluminum oxide and zinc oxide. And there you have it, my dear students. Remember this. The expert in anything was once a beginner. So don't be scared of this chapter. You've taken the first step today. Just keep revising these points smartly, and you will absolutely do wonderfully in your exams. I have full faith in all of you. All the very best.